In the next section, we'll be discussing how to remodel a learning problem. Let's review some ways in which a learning problem may be modeled. Image, video, and speech recognition traditionally involve the use of hand-built filters to parse out certain types of patterns from the data. The Sobel operator is a popular filter for edge detection in images, and the Hough Transform is a good filter for circle detection. However, given the complexity of the problem space and the richness of patterns, an approach that requires hand-tailoring filters doesn't scale, and furthermore results in inaccurate models. With the advent of deep learning, the problem of scaling was overcome. We now have highly accurate models. Deep learning methods are now state-of-the-art when it comes to image recognition. If your images don't have labels, one of the traditional methods for image segmentation is unsupervised learning, where one does the segmenting by training a model to recognize parts of an image that are similar to one another. What's another way to recast this? In the case of image segmentation, we can think of it as an optimization problem. Instead of training across large batches of images, you can optimize them individually, image by image. For any image, you can choose and iterate between a variety of segment configurations, and choose one where the difference between pixel intensities is the highest. Why is this relevant? Learning problems are trained by minimizing error between predictions and actual values across a large dataset. In other words, they're trained by optimization methods that are stochastic. But why is that? Learning and optimization problems have many things in common structurally. They both involve data spaces with a variety of variables, factors, or targets. In learning, parameters are adjusted iteratively over the course of training so that error is minimized progressively. In optimization, the solution is arrived at iteratively over the course of training so that the objective is improved progressively. Here's a key deciding factor to consider. If you optimize an image and start over for the next one, you're not generalizing anything. By this we mean knowledge gained about image interrelationships is lost between images. This, in essence, is the crux of learning methods. The idea is to invest time and computation up front so that downstream effort and inference is reduced. However, what if there's no need to generalize? If the problem scope is limited just to a particular set of images, optimization may be more effective. Alternately, for some problems, images may not have much in common, or have multiple key patterns that only occur once or a few times. In such scenarios, learning may be neither enough nor necessary. The same discussion largely holds true if this is recast as a search problem. It could work one at a time, but there is no generalization built in. Kato AI.